Good morning, everyone. So we're going to return to the very last topic in chapter 6, which is anomalous configurations. But before we go back to that very last slide that we were talking about in class on whatever day it was, Monday, I want to talk about the order that we fill electrons into when we're placing electrons into things like the 1s and the 2s and the 2p. One way you can know the order that you fill electrons into for electron configurations is just to use the periodic table. You just kind of go the element order from the 2s through the 2p, then through the 3s and the 3p, and then the 4s elements come next because that's our s block, and then we go through the d block, and then we go through the p block, so the 4p, and then back to the 5s, and it's 5 because we've already filled through the 4, and then we haven't yet gotten to the 4f, so we go through the 4d, then the 5p, then the 6s, and we finally get to the f block, our lanthanide series, and then we go through our 5d block, then our 6p, finally 7s, 5f, 6d, 7p. So you can get all of the ordering of the subshells that you fill into right from the periodic table. And then you can get these designations of 1s, 2s just by starting with 1 on downward for the s, and then starting with 2 on downward for the p shell, starting with 3 on downward for the d. And of course, the first time you can have an s is n1, the first time you have a p is n2, first time you have a d is n3, so that's why the first d is a 3d, the first p is a 2p, etc. And then the first f is L3, first time you have an L3 is n4, so the first f block is a 4f. So we can be filling in these labels and understanding why it's a 4f and not like a 6f or some other number. And then there's this principle that's not even in the book anymore. It used to be in the book a long time ago. It's in some other textbooks. You may have seen it in high school. And it's called the off-bow principle. And really, I think this principle is not really taught in our book anymore because it's just kind of like made up. But it's interesting that if you think of filling the subshells this way here, you get the order as well. So you'd fill the 1s, then the 2s, then the 2p, then the 3s. And then after you get through the 3s, then you're back filling the 3d. Excuse me, I missed one. So after the 3s, we fill the 3p, then the 4s, then the 3d, then the 4p, then the 5s. And that's the same kind of combination we had here, the 3d, then the 4p, then the 5s, and then the 4d, 5p, so the 4d, 5p, 6s. And then finally 4f, 6d, 4f, 5d, 6p, 7s, and then finally filling through the 7p. And then we never get to the 5g, so for your uncles worried about the 5g, we won't get there, with any elements on the periodic table. But they would come next if we had like an 8th row in the periodic table. So if we had an 8th row, then we'd probably going 8s, then 5g, then 6f. But we don't have elements big enough to get us into the 8th row. In fact, most of the 7th row elements have to be synthesized by bombarding protons and electrons into other nuclei, and a lot of times those nuclei only exist for a short amount of time. So when you get into these elements in this kind of range here, their lifetimes are going to be really, really short. And so a lot of them are only synthesized by man-made procedures and then don't last very long once they're made. Okay, and so then getting into the anomalous configurations. So anomalous configurations are the configurations that are different than what we expect. Let's make sure that we kind of see a lot of configurations are exactly the way we expect. And so our 3s1, 3s2, 4s1, 4s2, 5s1, 5s2, these are exactly as we would expect. So no anomalies in our s block. If we switch over to the p block elements, you can see these all go P1, P2, P3, P4, P5, P6, etc. So there's no anomalies within the P block elements. So within the S and the P block, sometimes we call that the main block elements. No anomalies there. But then we did see some anomalies in the transition metal series. And so the first row transition metals, there's only 2 anomalies that are different than what we expected. We would have expected chromium to be a 4s2 3d4, but it turns out to be a 4s1 3d5. You don't have to memorize this fact. You can just understand that there's a certain configuration that adds more stability for chromium. So there's just something about this configuration here of the 4s1 3d5 that's more stable for chromium than the 4s2 3d4. And then copper, same thing. It gains more stability through a 4s1 3d10. So having a half-filled or maybe a completely filled D subshell must add a little bit more stability, but not so that nickel jumped to a 3d10. Nickel stays as we expect, a 4s2 3d8. And so those are the only 2 anomalies in the first row. The second row actually has a bunch. We have molybdenum doing the same thing as chromium, We then have ruthenium and rhodium doing a peculiar configuration of moving one s electron into a d subshell for reasons that are hard to explain and understand, but they just happen to have these configurations. So again, we don't expect you to memorize the elements that have these anomalies, just that anomalies occur, but the anomalies aren't changing the electron count, just the electron location. So we would have expected this element here to be a 5s2 4d6, just like iron's a 4s2 3d6. We would have expected it to be the same type of configuration, but instead it moves one of the s electrons into the d subshell, so still has 8 valence electrons, just move them around, only 1 in the s block, 7 in the d block. So this would be our expected configuration, but it turns out to be a different configuration than we expect. And then rhodium does the same thing, and then palladium also has an anomalous configuration. So palladium has an anomalous configuration, so too does silver. And so then if we continue, like tungsten W doesn't have the same anomaly that chromium and molybdenum have, but then neither do osmium or iridium, but then platinum has an anomaly. And the thing that really strikes me with platinum and palladium and copper, so if you look at nickel, palladium, and platinum, they're all kind of different. Like nickel's exactly as we expect. Palladium moved 2 electrons from the s subshell into a d subshell, and then platinum for some reason moves 1 electron from an s into the d subshell. Makes no reason. There's really no rhyme or reason here for some of these anomalies. So no periodic behavior for that group. But then we do see that the one group, the copper group, does behave sort of periodically, where we get that periodic behavior where all 3 happen to have the same configuration. So again, no reason to memorize the ones that have the anomaly, but just trying to comprehend that there must be something about some configurations that adds some stability to them over the configurations that we would have expected. And then we do see a few of these in the F subshell. So lanthanum, for example, the first F block element should have been a 6s2 4f1, turns out to be a 5d1. And then cerium should be a 4f2, turns out to be a 4f1, 5d1. So it's putting 1 into an F, 1 into a D for whatever reason. So we would be expecting these to be a 4f1, 4f2, 4f3, 4f4. So praseodymium exactly as we expect. And then neodymium, exactly as we expect. So we're getting most of these then exactly as we expect. Gadolinium, though, has a slight anomaly. So it moves 1 out of an F. Should have been a 4F8. Turns out to be a 4F7, 5D1, for whatever reasons that make that configuration more stable. And then in the second row, we see a couple other anomalies for actinum, thorium, practinum, uranium, neptunium, and whatever that one is. So again, not to memorize, but just to kind of show that, and by circling, you kind of can get a sense that it's like not anywhere near half the elements in these groups that have these anomalies, but it's a few of the elements in the groups have the anomalies, but then the remaining elements are exactly the configurations that you expect. Now this element here just happens to be my favorite element. Does anybody know CF? It's californium. I don't know why, I just like the name of that one, just like, I don't know. So then a question that we might expect on this topic would be, not for you to memorize that chromium has the configuration of 4s1 3d5, but that if we give you, or if we say an element has this configuration, you should know it's chromium just by simply taking the 18 electrons that are in the argon configuration. So argon has 18 electrons, so there's 18 electrons in the argon configuration. That's the 1s2, 2s2, 2p6, 3s2, 3p6. So that's 18 electrons plus 1 plus 5. So that's 24 electrons total, and so element 24 is chromium. So this, in chapter 6, we're not talking about ions at all. So we're not getting into ion configuration. So if you see a configuration for an atom, it's for an uncharged atom, so therefore this has to be chromium. And so chromium has this configuration 4s1 3d5. How many total unpaired electrons does the atom contain? Well, there's one 4s orbital, there's 1 electron in it, so there's 1 unpaired electron there. And then I have the 3d subshell, for which there's 5d electrons, or 5d orbitals, and then I put 1 electron into each of those orbitals to maximize the spin. So I'm just applying Hund's rule and putting electrons in the same direction into these equal energy orbitals. So I end up with 6 electrons that are spin unpaired. So 6 spin unpaired electrons within this configuration of chromium. And that ends up being how you determine that this is the configuration of chromium. If you go into the lab and try to determine the number of unpaired electrons, which you can determine experimentally, chromium doesn't have the 4 that you would have expected, because you would have expected 4s2 3d4. That would have 4 unpaired electrons. It has 6. You get to 6 with this configuration here. I saw a hand going up towards the back, yeah.
Is that always going to be how you determine the unpaired electrons?
Yeah, so the way I would determine unpaired electrons is to think, well, how many 4s orbitals are there? Just 1. So there's just 1 4s orbital. And then how many 3d orbitals are there? There's 5. And so because there's 5 orbitals, I can put each one of those electrons into its own orbital, and then pairing them all in the same direction. Pairing them in the same direction is Hund's rule. So when we can, we maximize the spin of those electrons by pairing them in the same direction. One last thing I wanted to mention was going back to the count of valence electrons versus core electrons. I don't think I ever used the word core electrons. I just wanted to make sure to talk about that here within chapter 6 real quick, is that if we want to look at or count the number of valence electrons for an atom, so the valence electrons, let me zoom in a little bit. So the valence electrons should be the outermost. So the outermost shell electrons plus any electrons in a lower unfilled subshell. So for chromium, again, we have that argon configuration, 4s1 3d5. And so we have the outermost shell is n equals 4. So the shell is the n value. So the highest n, the outermost shell, is the 1 electron in the 4s. And then the D block here isn't filled. Filled would be 10 electrons. Once I put 10 electrons into the 3D subshell, then it would be totally filled. But as long as that's still empty or not totally filled, I count those electrons too. So I'd have 6 valence electrons for chromium. And then all the other electrons are going to be core electrons. So all the electrons that aren't valence electrons, these are all the other electrons. And so for chromium, 18 core electrons. So it'd have that argon core. So the 18 electrons as part of the argon configuration would be the core of the chromium atom. And so core would just mean the innermost, so the inner electrons, and then the valence, the outermost. So 6 valence electrons for chromium, 18 core. Okay, so I did put up a chapter 6 packet of questions. I'll get to those once we finish up chapter 7. So probably Friday we'll go through some of those chapter 6 review questions, and then we'll get into some chapter 7 review and probably a little bit more chapter 6 review next Monday. And so let's get into chapter 7 here. So chapter 7 goes from chapter 6 being about the electron to chapter 7 being about the nucleus. And so once you start seeing configurations and you start seeing a 1s1, 1s2, 1s2, 2s1, when you start seeing these different configurations, you may not realize as you're looking at the different configurations, you may say, well, is there a difference between a 2s1 configuration for lithium versus, say, a 2s2, 2p5 for fluorine? And we have to realize that there is a big difference between lithium and fluorine. Lithium is a metal, has a totally different set of properties than the element fluorine, where fluorine exists most stably at room temperature as a diatomic molecule, F2. That's a gas at room temperature. So completely different properties from left to right. And then once you kind of go past like neon and you get to that whole group of elements that share the property of being stable monoatomic gases, then you come back to being metallic again. So we have the idea that you have these periodic sort of trends for elements. And so where does periodicity come from? We're going to see it comes from some of the nuclear trends that if we look from left to right, there's a changing trend that then resets itself with each successive row on the periodic table. And then that's what allows each of the rows to have a shared set of properties. And so let's look at a quick demo. This is kind of like a classic chemistry demo where we put different metals into water and then see their different reactions. And then we kind of look for some similar trends for like the lithium, sodium, and potassium. I always find it funny that they give me safety goggles, not you guys. I'm going to go ahead and move this away from the front row, just so we're a little bit farther away. And then let me switch. Okay, so what I'm going to do is put pieces of lithium, sodium, potassium into some beakers of water, and then we can sort of see their similarities and then differences in reactivity trends. Okay, so let's start with lithium. So what I'm going to do is put a piece of lithium into the dish labeled for lithium. Oh wait, hold on. They already gave me some pieces that are out. So there's some pieces in these pieces of paper already. Okay, so what we see is a pink color forming, and we see the lithium dissolving into the solution relatively slowly. Lithium is reacting with water, and it's producing a hydroxide ion. So we're making lithium hydroxide, and they added some phenolphthalein to the solution. So we make the hydroxide ion, it turns that pinkish color. The actual reaction taking place isn't something we have to memorize, but alkali metals will react with water, and they are losing an electron into water, and at the same time, we're then producing H2 gas and then hydroxide ion. And so we're going to see that trend continue for the other, well, presumably the other alkali metals. So here is sodium. So it's reacting faster than lithium did. It's flying around the dish. But it's doing the same general basic reaction. So sodium metal is losing an electron. Losing electrons is oxidation, so it's oxidizing in water just like lithium did. So sharing that periodic trend. Now,
Is there a reason that it sizzles?
What's that?
Is there a reason that it's sizzling?
Well, we're going to see this better with potassium. So what's going on is we're making hydrogen gas, and hydrogen gas is flammable. The reaction is slightly exothermic. It's going to be more exothermic as we go down. So potassium is going to be a little bit more exothermic. It's going to react a little bit faster. So it's going to give off more heat, and it's going to probably ignite that H2. And so we're just kind of seeing the gas being given off is propelling that little piece around the tube. We're going to see when the gas is ignited at the same time with potassium, or presumably that's what we'll see. I hope that's what we see with potassium. That's why they give us a bigger container for potassium. And they give me a lid for it too. So, I think they may have forgotten the phenolphthalein. In fact, they gave me some. Let's see if that's the case. Yeah. So they just forgot to put the indicator in. So that's why it didn't turn pink. And they gave me one other piece, so let's see that one more time. Give me that in case it flies out, but it reacted faster than I can even put the lid on top. Okay, so potassium is just now reacting faster. And now there's a couple periodic trends that we can kind of see here. One is the idea that they react the same, but in a different rate. So lithium reacts the slowest, sodium faster, potassium even faster. If we get our hands on some rubidium, it would probably be super fun and crazy to see, probably be even more reactive. But they're doing the same basic reaction, so they're following that periodic trend. And then the other thing we might do is then compare the alkaline metals and see that they behave a little bit differently. So they're not going to react as quickly, and they're going to have their own set of properties because they're in a different group of the periodic table. I think something had flown into the magnesium already, though. So there's a little bit of something in the magnesium. It turned pink from something else. Same thing with the calcium. So when I add the metal to calcium, it's giving off some of the color. So calcium's reacting to produce some hydroxide ion. Looks to be a little bit slower than even lithium was. Magnesium doesn't look to be doing anything in the water. So magnesium doesn't react with water. Calcium does, but slower. So a different set of reactive trends. So a different group of elements behave differently, have a different set of properties. And so that's sort of like a basic demo into some of the similar properties of different groups of elements on the periodic table. And I would hope you guys had seen something like this before. Did you guys ever see like sodium into water in high school or in elementary, middle school? Ever? That's too bad. Okay, so what we want to try to do is try to understand, well, what are some of the periodic trends that lead to the periodic behavior, this periodicity for those elements? So The first topic in the chapter was just talking about the periodic table. Oh, let me switch. That is hilarious. That is just like now deciding to react pretty interestingly. It's like, I should probably put my safety glasses back. Maybe I'll move over here. Okay, so the first part of the chapter just brings up the periodic table, a little bit about the discovery. Not too much here to take away other than they show a little bit of the timeline of elements and when they were discovered. We've known about things like iron, copper, silver. So the elements shaded in gray, we've known about these elements the longest. So these are the elements that we were first separating from minerals and determining that you couldn't separate them any further. So if you think of that one slide out of chapter 1, can you separate a substance into simpler components? That's how we were determining and generating things like iron, copper, silver from sort of ores of these compounds from the Middle Ages. And then as time went along, we started to discover more and more elements. And then around 1870 is the development of the periodic table. So about 1870-ish is when Mendeleev is beginning to construct the periodic table by vertical columns of elements that share the same properties, and then also trying to leave gaps for elements that we didn't know about yet. So there are a lot of gaps in the periodic table, because if you look through right around this color here, and any of the shades in pink, green, this color here, so like your noble gases weren't yet known in 1870. A lot of elements weren't known in 1870 yet. That's when we first started putting elements together in terms of the periodic table. And then also X-rays were known at this time. You can bombard elements with X-rays, and then you can see a signature X-ray frequency for different elements based on their number of protons. So you can start to characterize the number of protons, or what later became discovered as the proton, and the nucleus is leading to the sort of frequency that was being observed in some experiments done by a scientist named Moseley. And this has sort of led to the idea of atomic number. And so atomic number is kind of discovered too. So we're putting elements in order of increasing atomic number, and then grouping by trends of similar properties. Then the question would be, what is the trend that gives you that periodicity? And it turns out that it's something called effective nuclear charge. So what is effective nuclear charge? Well, many of the properties of attraction, many of the properties of an atom come from the electron's attraction to the nucleus, and in particular the outermost electrons and how they're attracted to the nucleus. And so if we think, for example, about sodium, so sodium has that 3s1 configuration on top of neon. So if we're thinking of configurations and we write this one here, we would know from what we were talking about earlier that we'd have 10 core electrons. So we have that core of 10 electrons for neon, and then just one outermost electron. So we have a lot of inner electrons and then just one outer electron. And then as we start going from like left to right across a row, what ends up happening is the core stays the same. If you go from sodium to magnesium to aluminum to silicon, let's look at sulfur, let's think about chlorine for a minute. Chlorine would be the same neon core followed by a 3s2, 3p5, so we'd have 7 valence electrons. But we'd have that same core of 10 electrons. So the thing that elements have in common from left to right is they have the same number of core electrons, the inner electrons are the same. And it turns out that as you go from left to right, a lot more nuclear charge is going to leak out from the center of the atom to the outer valence electrons as you go from left to right, because the nuclear charge is increasing. So how much of that nuclear charge makes its way out to the valence electrons, and how much charge does each valence electron on average experience? And so the idea would be that sodium is experiencing a lot lower of a charge because it has those core electrons in the way. It has an 11 plus nuclear charge. That's the nuclear charge of sodium. It's element number 11, so 11 protons in its nucleus. And so it has 10 electrons in the way, so there's only about a 1 plus charge on average, or in that ballpark, that outer valence electron can experience. Whereas if you look at chlorine, chlorine has still that core of 10 electrons, but it has a nuclear charge of 17 plus. So about 7 plus of that charge can make its way out to the outer valence electrons. It's going to allow those electrons to be pulled in more closely. So it's going to allow chlorine to be smaller than sodium. From this one observation alone, we can probably predict that the radius of sodium is going to be bigger than the radius of chlorine. This just being the size of sodium is going to be greater than the size of chlorine. And you'll see that we use the radius of an atom as an idea of the size of the atom. So as the atom goes bigger, its radius is bigger. So sodium is going to be bigger despite having fewer electrons than chlorine, because chlorine has more charge to pull those electrons in. And so then imagine as you go from left to right, you're going from sodium to magnesium to aluminum. The size is just decreasing as you go from left to right. And then when you get back to potassium, you jump back to being big. And you reset that trend. So the alkali metals have this trend of having that one electron that's not held onto very strongly. And then you can even get a sense that from this demo here, which electron, lithium's one electron is one valence electron, or potassium's one valence electron. Which one do you think is held onto weaker? So lithium versus potassium. Potassium reacted a lot faster, probably because the electron was easier to rip off. So potassium's ionization energy, we're going to see, was dropping, was lower than lithium's. So if we compare the ionization energy is the energy it takes to remove an electron. So this is the energy associated with things like lithium going to lithium plus an electron, or potassium going to potassium plus an electron, that the ionization energy is going to show a strong dependence on this effective nuclear charge trend. So the ionization energy, you can sort of get a sense that this ionization energy of lithium is probably going to be a little bit higher, and potassium is going to be a little bit lower, because that's why potassium is reacting faster in our demo and our demonstration than lithium. So we'll get to the trend for ionization energy later, but you can maybe get an appreciation that we can see the effects of the top to bottom trend, or how ionization energy changes from top to bottom from that demonstration that we looked at where potassium is reacting faster. It was just losing its electron more easily. And we're going to see that it has a little bit to do with it being bigger, and there's some other trends that we can look at too with that ionization energy trend. If we think left to right, if we go back to sodium versus chlorine, so you have sodium versus chlorine. Which atom do you think is going to be easier to remove an electron from? Sodium, big nucleus, only experiences a 1+ charge, or chlorine, smaller, where the electrons are closer to that higher charge? Chlorine's ionization energy is going to be a lot higher. So if you compare, say, sodium going to sodium plus an electron to chlorine going to chlorine plus an electron, that the ionization energy of sodium is going to be a lot smaller than the ionization energy of chlorine, due to that charge trend, due to that effective nuclear charge trend. That sodium's nuclear charge, the nuclear charge the outer valence electrons experience is lower than chlorine. Chlorine's smaller too. So there's a lot of cross dependence that we'll see size has on the effective nuclear charge trend, and the same thing with ionization energy. Now we'll go through these trends one at a time. So this is giving a quick little introduction into the topic. So let's look at this trend here, or look at this slide. So effective nuclear charge effective charge is the charge experienced by the valence electrons for an atom, or by the shell of the electrons that we're considering within an atom. And we can approximate that by taking the Z minus whatever the screening factor is by the other electrons that are smaller than the electrons that we're considering. And so we can take Z minus the core electrons to be one approximation method for giving us the effective nuclear charge. So for sodium, this would kind of work like this, where we have the Z for sodium would be 11. This is the number of protons in the nucleus. So Z is just the nuclear charge. And then the number of core electrons for sodium is 10. And so the Z effective approximately for sodium is +1. The Z effective approximately for potassium would be about +1. So as you look down the alkali group, they're all approximately +1. We're going to see there is a trend though. They're not exactly +1, but approximately about +1. And then if you look at the alkaline group, they're about +2. If you look at the boron group, they're approximately +3. So from left to right, what's changing is that effective charge is increasing from left to right. Now, one thing that you can look at is if we go back to some of these radial probability diagrams, if you look at something like, say, the 2s orbital, or the 2s probability function, that the s functions and all functions have some probability of being relatively close to the nucleus. So we'll see how that plays a role in effective charge as we kind of continue. So when you think of the effective charge of an outer electron as you go from top to bottom, we'll try to think about how diagrams like that can help us understand the top to bottom. So let's look at effective nuclear charge in a few different ways. One is, let's look at the effective charge but experienced by the s electron. So if we're looking at sodium, let's go back to sodium as an example. So we have and let's go to its full configuration. So 1s2, 2s2, 2p6, 3s1. And so you can sort of think on the level of which electrons experience the highest charge overall for this one atom. So the 1s electrons experience the greatest charge, and they're like absorbing some of the charge and not allowing it to make its way out to the outer electrons. And then presumably the 2s would come next, then the 2p subshell, and then followed by the 3s, meaning the 3s subshell experiences the lowest nuclear charge, and then the 1s experiences the highest nuclear charge. So the outermost experiences the lowest charge, the innermost electrons experience the highest charge. And so what the red curve here is using an advanced method to calculate the charge experienced by the 1s shell for the elements lithium, beryllium, all the way through argon. And if you notice, they're experiencing about the full nuclear charge. So the 1s subshell is experiencing almost the complete nuclear charge. And then you can see it's dropping off a little bit. Why might it drop off a little bit? Well, it's dropping off a little bit because of how every other subshell has a little bit of a probability of those electrons being relatively close to the nucleus. And so as you go further away, there's more and more subshells that have a little tiny probability that those electrons are sort of close to the nucleus, and they're experiencing a little bit of that positive charge, taking it away from the 1s subshell. If you use the approximation that we just mentioned, that we can take Z as the Z minus S, where S is the number of core electrons. If you use the core electrons as an approximation, you get this green curve. You get this green curve, and what's nice about the green curve is it shows you periodicity. It shows you that for lithium on across to neon, that effective charge increases consistently from left to right, and then when you get back to sodium, it drops back to +1, and then goes back to increasing from left to right. And so the trend that repeats itself in the periodic table is effective charge. So we start low on the left side, we go to high effective charge on the right side, and then we reset that trend. This is why we're going from metallic elements across to non-metallic elements, and eventually getting to the noble gas group of stable monoatomic gases. And so this is our resetting trend. So the resetting trend is periodicity. So periodic behavior comes from that resetting of the effective nuclear charge trend. Now, when you look at more advanced methods, the blue and the yellow curves are just using more advanced methods, neither of which I think are worth dwelling too much on what exactly those methods are. But from the more advanced methods, you can see a little detail. That is, the effective charge is whenever you reset each row, actually reset to be a little bit of a higher charge. And so when you reset the effective charge, each time you go down to the next row, it's a little bit higher than it started off at in the previous row. So in other words, if you start approximately +1 for lithium, go across to approximately +8 for neon, when you reset for sodium, it's going to have a slightly higher charge than +1. And the slightly higher charge from +1, there's a few ways we can try to understand why that trend is the way it is. But one thing we can try to do is just understand that trend. That the trend from left to right is that we get the increasing effective nuclear charge for the outer valence electrons from left to right, and this resets with each row. So with each new row of the periodic table, we reset back down to a low effective charge, then increase back towards the noble gases with the highest effective charge from left to right. And then the core electrons, as we go to larger and larger rows of the periodic tables, we go from having a core of 2 versus 10 versus 18, the larger cores are allowing then the larger valence shells to have a higher probability of electrons being relatively close to the nucleus with each successive row of the periodic table. So for example, for potassium, you have the 4s orbital as its valence orbital. And then you have this sort of like diagram that we were going over for the radial probability function, that you have all of these probabilities of the electron being relatively close to the nucleus. Those just start to add up. And so this is giving you a little bit of a higher charge due to those electrons being relatively closer to the nucleus on average. And so this gives you a slight increase in effective charge from top to bottom. And then we'll just have to see how that trend plays out with some other trends, like the size trend that we'll go over in a moment. So as you think about effective charge, from left to right, the size should decrease because we're pulling electrons in more closely with that higher charge. And then if you think left to right, the energy it takes to remove an electron should increase because the electrons, again, are smaller, closer to the nucleus, to take more energy to remove those electrons. Okay, so let's think about some size trends for atoms and how left to right trends emerge from periodic behavior of the effective nuclear charge. But let's also talk about a consequence of bonding versus non-bonding. So what we're showing here is the difference between, or trying to think about the difference between a non-bonding radius. So if we imagine making a radius of whatever this molecule is, I think this is chlorine, or you can picture this as 2 chlorine atoms. You can imagine the sort of topic or the question that chlorine atoms have a particular non-bonding radius. If they're not making a bond with each other, they'd have a certain size. And then if you make a bond, those atoms are going to overlap with each other. And then the bonding atomic radius is going to be shorter than the non-bonding radius. This is only a consequence really for elements like the noble gases that don't form bonds or don't commonly form bonds in a way that you can measure their bond lengths. And so for certain elements like the noble gases, they're only going to have a non-bonding atomic radius. The bonding atomic radius is always going to be a little bit shorter than the non-bonding radius. So when we make a bond, bonds go a little bit shorter. So the bonding atomic radius would just be the distance separating the nuclei divided by 2. So if you divide this distance by 2, that's our bonding atomic radius. I only mention this because in this slide here, we're seeing a trend for bonding atomic radius. So we're seeing a trend from left to right towards the halogens for bonding atomic radius. And we're seeing this for single bonds, which we don't know too much about bonding type, or at least I haven't taught you much about how to predict bond type from single versus double versus triple. And so this is showing us the relative size that atoms would have if they make single bonds with other atoms. And so, for example, the size of oxygen, 0.66 angstrom. So if you had a water molecule, you'd be predicting water, the bonding atomic radius of hydrogen, 0.31 angstrom. For oxygen, 0.66 angstrom. So our bonds in water, we'd expect to be about 0.97 angstrom. And so you could use this chart to predict bond lengths, but really the better use of this table is just the idea of changing of size of an atom from left to right. And so as you go from left to right, as you go from lithium towards fluorine, size goes smaller because the atoms are experiencing a higher charge. Charge pulls those electrons in more closely, the atoms become smaller. And so we have a decrease in size from left to right, and that's because the effective charge is increasing with that same trend. You have a higher charge, the positive charge pulls the negative electrons in more closely due to the electron nuclear attraction. So if you're thinking of a 2s versus a 2p subshell, think of there being negative particles being pulled into that positive charge. So just always think the electron's negative charge, nucleus positive charge. That's why we get this decrease in size. Now, one thing to point out, notice how the noble gases are all bigger than fluorine. Why did the trend not continue of decreasing size through the noble gases? Well, this is a nuance. You're going to see there's lots of nuances when we look at trends. The nuance for the noble gases is they don't make bonds. So we're comparing like a bond length trend, a bonding atomic radius for the one set of elements, but then because the noble gases don't make bonds, this is the non-bonding radius, which if you recall is bigger than the bonding atomic radius. And so we're just not really comparing like fluorine versus neon in a way that allows us to get a good comparison of their size. So we're really not trying to say fluorine atom is smaller than neon. What we're trying to say here is that a fluorine atom making a single bond would be smaller than neon. So think about the trend of size decreasing through the noble gases. If you're comparing the non-bonding radius of fluorine versus neon, fluorine's going to be bigger, neon's going to be smaller. We see a little bit of a nuance in the trend with this table because it's showing us the trend for bonding atomic radius, but for the elements that make bonds. And it's showing us a non-bonding radius for the elements, the noble gases that don't make bonds. So a little nuance, but nothing to worry too much about. And then what about the top to bottom trend though? This one I think makes a lot of sense. If you look at every group, you get an increase in size from top to bottom. And this is because you're using more and more larger orbitals. So if you go from a 1s1 to a 2s1 to a 3s1 configuration, we're going to larger atoms. So each successive row of the periodic table resets itself with a new effective charge and a larger size. So lithium is smaller than sodium. Sodium is smaller than potassium, or another way of thinking of it is sodium is bigger than lithium, potassium is bigger, rubidium is even bigger. Now, one of the things we're going to have to think about for ionization energy trends is how charge interacts with distance. And so we've used this equation before, Q1, Q2, divide by D, that this times a constant, which we never really throw math into this equation. This is more of an idea equation. This is the energy of electrostatic attraction equation, or Coulomb's law. So as the charge of particles that are opposite in charge, so you need two particles to be opposite. You have the negative electron, the positive nucleus. So there's attraction built in. So as long as you have negative, positive, we have attraction. And then the higher the magnitudes of charge, the greater the attraction. So if we can make the magnitudes of charge increase, then we would increase attraction. And if we can make the ions closer, then they get more attracted. So being closer together with the charge allows the ions to be more attracted together. As we imagine going from sodium to potassium, or the lithium, sodium, potassium trend, the electron's moving further away from the nucleus. This is the term we're going to see that really dictates why it is that potassium was ionized more easily, the electron was lost more easily than it was for lithium. Because the electron's so much further away, held on to more weakly. Okay, let's think about the size though of ions. So how does an ion size compare to its uncharged counterpart? So if you imagine comparing sodium versus sodium plus, that it probably isn't too hard to think. If you go from a 3s1 configuration, you lose the 3s1, you only have your core, that cation has to be smaller. So cations are always smaller than their uncharged parent atoms, if you will. So sodium is going to be bigger than sodium plus in terms of its size, so the radius of sodium bigger than sodium plus. And so just think of this as going from a neon 3s1 for sodium to just the neon core. So if you have a 1s2, 2s2, 2p set of orbitals, followed by 3s1, you lose the 3s1, you lose a lot of size. So if you look at the size difference between sodium versus sodium plus, pretty big difference here, that sodium plus is a lot smaller. Magnesium 2 plus is a lot smaller. You lose 2 electrons, you lose a lot of size. So magnesium 2 plus a lot smaller than magnesium ion. But we could even say that magnesium with a positive charge would be smaller than magnesium with a 2 plus charge, even smaller. So lose 1 electron off magnesium, smaller. Lose a second electron, even smaller. What about anions though? What about if you go from having, like, say, fluorine to F minus? What happens here? So as you go to F minus, you add in extra electrons to the mix. Electrons repel each other. The size grows bigger. So anions are always larger than their neutral counterparts. So anions do the opposite. You have an atom, take an electron away, go smaller. If you take an atom, you absorb an electron, you go bigger. So if you look at the case of elements where it's more common that they absorb electrons, fluorine to F minus grows a lot in size. Notice that F minus is actually a lot bigger, almost double the radius, or more than double the radius. O2 minus, a lot bigger than O atom. S to S2 minus, sulfide, a lot bigger than sulfur. So every time we're adding electrons, we're increasing the size of the ion. So anions grow larger than their neutral atoms, and then cations grow smaller than their neutral atoms. Well, what about if we're comparing atoms then that have the same number of electrons? So what if we're comparing O2 minus? O2 minus has 10 electrons. F minus has 10 electrons, because we started with fluorine with 9 electrons, added -1 for the charge, go to 10 electrons. So it's kind of like making sure when we see O2 minus, oxygen should have 8 electrons plus 2 for the extra negative charge for 10 electrons. So making sure that you see how it is that oxygen, or O2 minus as an ion, has 10 electrons. So O atom has 8 electrons, O2 minus has 10 electrons. F atom has 9 electrons, F minus therefore has 10 electrons. Sodium plus has 1 removed from sodium, so that's 10. Magnesium 2 plus also has 10 electrons. These all share having the neon core. So all of these configurations are that of neon. So oxygen gained 2 to get neon's configuration, fluorine gained 1 to get the neon configuration, sodium lost 1, magnesium 2, aluminum 3. If you think about the size trend here, which of these ions do you think is the smallest? Like aluminum or oxide ion? I mean, it's on the chart, but if you think about it, it's going to be the one with the highest charge. So if you're looking at having a 1s2, 2s2, 2p set of electrons, and these are all negatively charged particles, Which ion do you think is going to be the smaller one? The one with the 8 plus charge or the one with the 13 plus charge? More positive charge, the closer those electrons are pulled in. So having a higher number of protons, having a higher nuclear charge, allows aluminum to be a lot smaller. So Al3 plus, 0.68 angstrom. So this is smaller than magnesium, smaller than oxygen. Notice that F minus is bigger than sodium plus. And then O2 minus even bigger than F minus. We call this an isoelectronic series. So when you're comparing size of atoms, you got to do two things. Either we compare the size of uncharged atoms using the bonding atomic radius trend, the general trend of size that we brought up a slide or two back, or we're comparing the size of ions, which we try to use what we call an isoelectronic series. We try to think of having ions that have equal number of electrons, how might they differ in size? And so if we want to compare sodium to fluorine, this here is bonding atomic radius trends. This is just our general trend for size. So we're just using size decreases left to right. So from left to right, size decreases. Wow, where's the erase button? So size decreases left to right, and then increases top to bottom. And so from sodium to fluorine, how does sodium to lithium to fluorine compare? So what I would do here is compare sodium to lithium, because that's directly above each other on the periodic table, and fluorine's over here. And so for the size trend, I would be thinking sodium's bigger than lithium, right? From top to bottom, size increases. So size increases from top to bottom. So sodium's bigger than lithium, and then lithium is bigger than fluorine because size decreases left to right. So for uncharged atoms of sodium versus fluorine, sodium is going to be a lot bigger than fluorine. Okay? If we're comparing sodium to sodium plus, remove the electron, of course sodium plus is smaller. Fluorine, add the electron, the F minus goes bigger. And then when we compare the two, we're then comparing they both have 10 electrons. And so then we're looking at the Z's. Sodium's element 11, sodium's element 9, so 9 protons for 10 electrons for fluorine. For F minus, so F minus is bigger than sodium plus. So do you see how sodium's bigger than fluorine uncharged? So they each have their normal count of electrons on the periodic table. Sodium's bigger. But if you add an electron to F, it goes bigger. You take an electron away from sodium, it goes smaller, such that Na plus is smaller than F minus. Now, how does ionization energy compare as we maybe go left to right or even within an element? Let's first look within an element itself. So we can look at an element's first ionization energy compared to its second ionization energy compared to each successive ionization. If we maybe use magnesium for an example here. So magnesium's first ionization is magnesium to magnesium plus an electron. All these energies you see tabulated in this chapter. If you see an energy in the first half of chapter 7, it's for the gaseous atom. So magnesium as a gas converting to magnesium plus as a gas plus an electron. This ionization energy is given in this chart here. That corresponds to 738 kJs per mole. Because that's the first ionization energy of magnesium. So the energy it takes to remove one electron from magnesium is 738 kilojoules per mole. Now, let's first think about something. Remember how, we talk about magnesium going to magnesium 2 plus is favorable, sodium forming sodium plus is favorable, but you see that energy is still required for these atoms to lose that electron. So ionization energies are still always positive. It takes energy to remove the electron. The atom has to absorb energy to break the attraction that the electron has to its nucleus. And so it takes 738 kilojoules for the first electron. If you try to take the next electron off, it takes even more. So each successive electron is going to take more energy. Why is that? Well, if you take an electron off magnesium, what happens? It goes smaller. So the last valence electron of magnesium is now closer to the nucleus. Closer to the nucleus, more energy to remove. So we're just kind of thinking that kappa Q1, Q2 divided by D, if you decrease the distance, you increase the energy of attraction, takes more energy to remove. And so the I2 of magnesium is 1451. And that's higher. So the second ionization energy, So the first one's the I1. The second reaction is the I2, is the second ionization. So it's the energy just to remove the second electron off of what's left after the first ionization. So it's the magnesium plus, technically as a gas, not a big detail, but these are all gaseous atoms, so that you don't have any goofy solid trends or anything going on here. The third ionization for sodium, which you might be saying, well, this probably isn't going to be something magnesium would do, but it's something you can measure experimentally. And you can measure this value experimentally. The I3 of magnesium, you would probably expect this to be really high, because now we're removing a core electron. So we went from a big S electron to then a smaller S electron to now an electron very close to the nucleus. This takes a lot of energy for magnesium. That is 7,733 kJs per mole. So you get this huge increase whenever you remove a core electron. So core electrons take a lot of energy to remove because they're a lot closer to the nucleus. And so if you take a look at our chart here, you can see that sodium has a relatively low I1, and then it has a really high I2 because the I2 corresponds to removing one of its core electrons. If you notice magnesium that we just went over, higher than sodium. So think about sodium to magnesium. Sodium to magnesium. Magnesium is smaller than sodium. So magnesium starts its S electrons closer to a nucleus with a higher effective charge. So compared to sodium, what happens here? The Q increases and the distance decreases. Both of those say the ionization energy should go up. And so ionization energy goes up for magnesium. The second ionization energy higher than the first. And then the third is what's really high for magnesium. Now, aluminum looks a little bit deceiving when we think about size trends or just the charge trend. So as we go from magnesium to aluminum, the effective charge does increase. So the charge goes up, but we have a weird anomaly where we have a bigger P subshell. So the P subshell turns out to be bigger than an S subshell. And so we get a weird zigzagging trend for ionization energy where it'll go up for the first two elements, and it'll drop for the third, then continue to go up, and then be about the same or maybe a little lower for the next element. So this would be like sodium, magnesium, aluminum, silicon, phosphorus, and then sulfur, chlorine, argon. And so the NP1 and then the NP4 elements are a little bit lower than you expect due to some weird anomaly. So remember how we had an anomaly for the noble gases having what looked like a bigger size. If you're using ionization energy for nuclear attraction, we just have a difference of what type of subshell electrons are being removed. We're going from removing an S subshell to a P subshell. P subshell is just a bigger orbital. Takes a little less energy to remove the P orbital electron compared to the S electrons for sodium and magnesium. So you have a little bit of a resetting of the trend, and then it continues to increase. A little resetting here because of spin pairing. Not a big detail on why the NP4 is lower, but we're removing an electron that was spin paired, which is destabilizing, so you get back some of the destabilization, so it's not as high as you may have expected. But then if you look at, again, for each of these elements removing a core electron, it's a big jump of energies. Like each successive electron is about double, and then when you get to the removal of a core electron, it's about an increase of about 5 or so. So let's look for, say, sulfur. So sulfur, I1 to I2 doubles, or about doubles. About again for the third, about again for the fourth, about again for the fifth. 6 is the last. Sulfur has 6 valence electrons, so the 6 valence electron kind of falling in suit of about 1,000 to 1,500 kJs per mole per electron. And then notice that we go up to 27,000 for its core electron. So a huge increase for the removal of a core electron from an atom like sulfur. So the core electron removal is always a lot higher energy compared to the other elements near it. And so I just wanted to end with this slide here. This is just kind of showing you that trend I was talking about, how you get a little bit of a drop, then an increase, a little bit of a drop, then an increase. So increase, a little bit of a drop, followed by an increase. And this break in the trend is just kind of a footnote in a way, because we really want to use ionization energy just to try to understand how does that increase in charge, decrease in size impact the attraction of nucleus. We can sort of measure that through ionization energy, but it's just a little bit nuanced. It's nuanced in the MP1, the MP4 column. And so we'll pick up and go back over some of these other trends here. So we'll start from this slide next time and talk about our top to bottom trends. But generally left to right increasing. And then we'll point out next time why we get a slight decrease from top to bottom. It's a little bit of a decrease, but we'll point out next time why that is. All right, guys, have a great day.